identified. The second type of reaction we're going to talk about is a redox reaction or oxidation reduction reaction. They involve the transfer of one or more electrons between reactants. The rusting of iron is an example of a redox reaction. The solid elemental iron, in the presence of oxygen, has been converted into the compound iron oxide. The iron has been oxidized and the oxygen has been reduced. In a redox reaction, electrons are transferred from the species that is oxidized to the species that is reduced. The substance that loses electrons is oxidized, and the substance that gains electrons is reduced. We have a mnemonic device to help us with this. Leo the lion says grr. Leo means the loss of electrons is oxidized, and grr means the gain of electrons is reduced. The oxidation of one substance is always accompanied by the reduction of another substance. Oxidation numbers may be assigned to each of the atoms in the reactants and products, and this is often an effective way to identify redox reactions and what's oxidized and what's reduced. Atoms in their elemental form have oxidation numbers of 0. Examples include hydrogen, iron, oxygen, calcium. Monatomic ions have oxidation numbers equal to their charge. Example, lithium, the lithium plus 1 ion has an oxidation number of 1. The sulfide ion has an oxidation number of -2. Hydrogen ion has an oxidation number of +1. Oxygen in a compound most often has an oxidation number of -2. One notable exception is peroxides like H2O2, where oxygen has an oxidation number of -1. Hydrogen usually is +1 when it's bonded to a nonmetal and -1 when it is bonded to a metal. And fluorine always has an oxidation number of -1. When we look at oxidation numbers in compounds, in neutral compounds, the oxidation numbers must add up to 0. In polyatomic ions, the oxidation numbers must add up to the charge on the ion. If we look at some practice here, first H2O, we know hydrogen has a +1 oxidation number and oxygen has a -2 oxidation number. When those add up to the overall neutral charge on the compound with those 2 hydrogens and the 1 oxygen. Carbon dioxide, oxygen has a -2 oxidation number. And for 2 of those oxygens, there'll be a -4 overall. Carbon must have a +4, so its oxidation number must be +4. In sodium nitrate, oxygen has a -2 oxidation number. Sodium has a +1. And that means there are 3 oxygens, each at -2, so -6. The 1 sodium, it allows us to determine that the nitrogen has a +5 oxidation number. And in the sulfate ion, oxygen, of course, has a -2 oxidation number. There are 4 of those, so -8. The sulfur must be a +6 in order to get that -2 overall charge, and so sulfur has a +6 oxidation number here. Precipitation reactions are the third type of reaction. 7. So let's briefly go over that now. In a redox reaction, electrons are transferred from one species to another. The substance that loses electrons is oxidized, and the substance that gains electrons is reduced. The oxidation of one substance is always accompanied by the reduction of another substance. And balanced chemical equations for redox reactions can be constructed from looking at half reactions. If we look at this example, when aluminum is placed in an aqueous solution of copper 2 chloride, the products are aqueous aluminum chloride and solid copper. The reaction is represented below. The above redox reaction can be separated into 2 half reactions. First, we need to figure out what's oxidized and what's reduced. You may recall that oxidation numbers for elemental substances are 0, and monatomic ions are the same as their charge, and so we can assign our oxidation numbers as such. Inspecting those and using our mnemonic device, Leo the lion says grr, we can see that aluminum goes from a 0 to a +3 and is oxidized, and copper goes from a +2 to a 0 and is reduced. Now we can write those half reactions. So if I take the species that was oxidized, so the solid aluminum and the aqueous aluminum ions on the reactants and products side, and construct a half reaction, I know that the number of electrons lost in that process is 3 electrons if I inspect those oxidation numbers. I can do the same thing with the reduction half reaction and see that copper gained 2 electrons to become solid copper. Those half reactions can be used to develop the net ionic equation for the balanced redox reaction. So the oxidation half reaction shows the loss of 3 electrons as aluminum was oxidized, and the reduction half reaction shows the gain of 2 electrons as copper is reduced. In an oxidation reduction reactions, the electrons lost by one species must equal the electrons gained by another species. And in order to do this, we multiply each half reaction by the appropriate coefficient and combine those two half reactions to write the overall balanced net ionic equation for the redox reaction. Here I can see that 3 electrons were lost in the oxidation half reaction and 2 electrons were gained in the copper reduction half reaction. So I'm going to multiply those equations, those half reactions, by the appropriate coefficients and then combine those half reactions into one balanced net ionic equation. I see that my electrons lost and gained are equal to one another, and those can cancel out. And there's my balanced redox reaction. Let's look at an example. The half reactions for the oxidation reduction reaction between chromium and silver plus 1 are represented above. We want to find out which substance is being oxidized and which is being reduced, and then write the balanced net ionic equation for this redox reaction based on the half reactions. First, we want to see that chromium is going from a 0 to a plus 3. And so it's being oxidized, and silver is going from a plus 1 to a 0, and it's being reduced. So now I know which substance is oxidized and reduced. Next, I'm going to write the balanced net ionic equation using those half reactions. Remember that the number of electrons lost and gained must equal one another. So I've got to multiply the oxidation half reaction by 1 and the reduction half reaction by 3, and then put those two half reactions together and see that my electrons cancel on both sides. Let's practice this. So please read through the question, pause the video, answer the question, and then play the video to check your work. This reaction, we have half reactions for the oxidation reduction reaction between cobalt and silver plus. We want to find out which substance is being oxidized and which substance is being reduced. Again, we can see that cobalt is going from a 0 to a plus 2, it's being oxidized, and silver is going from a plus 1 to a 0, it's being reduced. Next, I want to write the balanced net ionic equation for the redox reaction. So I'm going to look at the electrons lost by the oxidation reaction and the electrons gained by the reduction half reaction and make sure those are equal. So if I multiply the oxidation half reaction by 1 and the reduction half reaction by 2, I can combine those two half reactions and see that the electrons lost and gained is equal to one another. And there's my balanced redox reaction.